Now let's talk about raster proximity analysis, where we analyze relationships between adjacent and nearby cells. We can categorize raster proximity analysis into four general categories: resample, generalization, interpolation, and density. Resample changes the spatial resolution of a raster dataset, and you can find the resample tool in the data management tools toolbox in the raster processing tool set. Generalization removes unnecessary detail. Interpolation predicts cell values at unmeasured locations between measured points. And density maps the highest and the lowest concentrations of features. You can find generalization, interpolation, and density geoprocessing tools in the Spatial Analyst Tools toolbox in the Density, Generalization, and Interpolation tool sets. Let's explore each of these raster proximity analyses, starting with resample. We use resample to change the spatial resolution of a raster dataset. And there are four standard techniques we use when we resample data: nearest neighbor, bilinear, cubic, and majority. Nearest neighbor assigns the value from the closest cell, and we use it for categorical data where we have discrete categories of data. The data often looks a little pixelated, but it has good, clean definition between the different categories. Sometimes we want to generalize our categorical data even further, and we'll use majority, which assigns the most popular value from surrounding four cells. Now, both of these types, nearest neighbor and majority, look pixelated. When we're looking at image data, we don't want it pixelated. So for image data, we use bilinear, which interpolates values from surrounding four cells and smooths the image data. Last, for continuous measurement data like digital elevation models, we want to smooth and sharpen the image. And so we use cubic, which interpolates the value from surrounding 16 cells. Now there are three different approaches in ArcGIS Pro to resampling your raster data: resample rendering, resample function, and resample geoprocess. Resample rendering is applied directly to the raster layer in your map view. And so you access resample rendering from the contents pane. You select your raster layer, you activate the raster layer ribbon, and then you click on the resampling type drop-down button and select your technique. The resample function creates a copy of the raster layer and applies the resample to the copy. You can access the resample function from the analysis ribbon, where you can access the raster functions and find the resample function. Last is resample geoprocess, which actually creates a new raster data set. And you can access the resample geoprocess from the data management toolbox in the raster and raster processing tool sets in the resample geoprocessing tool. And if you look at the resample geoprocessing tool, you can see one of the parameter values is an output raster data set. So you're actually resampling the input and creating a whole new raster data set. Now, which approach you use depends on your goals. If you just want to look at your data, you're going to typically use resample rendering. But if you're going to experiment with a workflow, for example, before you create output, you might use resample function. And last, when you know what you want and you want to create a whole new raster data set, you're going to use resample geoprocess. Generalization analyzes relationships between adjacent and nearby cells. We use the aggregate geoprocessing tool to decrease cell resolution. So the input raster is the raster to be generalized, and then we set the output raster and the cell factor by which to multiply the input raster cell. For example, a cell factor of 3 would result in an output raster cell size 3 times larger than the input. And if you look at the example on the right, you can see I have my input raster, which is a much higher resolution than my output raster. So in this example right here, I must have a cell factor of 3. So it's aggregating the 9 cells in the upper right-hand corner to the single cell, which is a 3 in the output raster. We use the majority filter geoprocessing tool to generalize cell values. The input raster is the raster to be generalized. In the output raster, the values are replaced based on neighboring cells' majority values. So again, look at the example on the right. You can see I've got my input raster, and then I use the majority filter to kind of clean it up so I have a less fragmented or speckled looking raster. And so notice how the majority filter affects the sevens in the input raster and output raster. The sevens are a little bit fragmented, and the majority filter has generalized those areas in the output. We use interpolation to predict cell values at unmeasured locations between measured points. So we estimate unknown values that fall between known values. If you look at the example on the right, you can see that my input known values are a point data set with values assigned to them. And I utilize that to interpolate or predict the values between the sample points to create a continuous raster data set in this case. So if you look at the lower right-hand corner of the raster data set, I've got two sample points, 10 and 11, and the geoprocess interpolates the values between those known points, the same as between sample points 9 and 10. Now, interpolation assumes spatially distributed objects are spatially correlated. That means that cells are located within close proximity to each other are more likely to be close in value, and cells that are located a long ways from each other are more likely to be less close in value. For example, temperatures recorded at weather stations will be similar to temperatures nearby, but they won't be similar to temperatures that are recorded across the country somewhere. Another example is crime is more concentrated in some neighborhoods than others. So if you have a neighborhood where there's existing crime, there's more likely to be crime close by as opposed to a neighborhood where there is no or little crime associated with it. Now, there are two types of interpolation that we'll discuss, including deterministic and geostatistical. Deterministic interpolation predicts cell values based on the extent of similarity or the degree of smoothing. The values of closer points are weighted more heavily than those further away. And they can be divided into exact interpolators and inexact interpolators. Exact interpolators predict values identical to the measured value at sampled locations. And so if I measure a value of 10, then the cell value that corresponds to that location is also going to be a 10. And the types of exact interpolators that we have access to in ArcGIS Pro are inverse distance weighting, or IDW, spline, and natural neighbor. An inexact interpolator predicts a value that is different from the measured value, in which the sample point might be a 10, but in the corresponding raster surface, that location might be a 9 or 11. And the geoprocess that we utilize that as an inexact interpolator is a trend. And you can find all of these interpolation geoprocessing tools in the Spatial Analyst toolbox in the interpolation toolset. Now, IDW is a deterministic interpolator that predicts cell values based on the extent of similarity. And so the closer you are to the input sample points, the more likely the value is going to be similar to those sample points. We use IDW for dense, evenly spaced sample points with a normal spatial distribution. It's kind of my go-to interpolator that I'll use to generate a raster data set, and then I'll look at the results and make sure that it works. If it doesn't, then I tend to fall back on some of the other interpolators. IDW applies a linearly weighted combination of sample points within the search radius to predict cell values. Weight is a function of inverse distance away from the sample points within those search areas. The power parameter lets you control the influence of known points on the predicted values. I typically don't play with the power parameter too much unless my output raster really doesn't represent the surface that I'm trying to generate. Of course, IDW is an exact interpolator that creates raster surfaces with more detail and are less smooth. In the example on the right, I'm trying to create an elevation surface, and you can see I've got sample points with elevations spread across my area that I'm going to utilize to create a continuous raster data set. And so how IDW works is it's trying to predict the value, for example, at the yellow dot, and so it uses the search radius, which is the yellow ellipse, to identify all the sample points within the search radius, in this case, the red points. And the red points that are closer to the location I'm trying to predict have more weight than those that are further away. Another deterministic interpolator that predicts cell values based on the extent of similarity is natural neighbor. I use natural neighbor geoprocessing for connecting sample points with a smooth surface created from Thiessen polygons. The geoprocess applies a Voronoi diagram, which are Thiessen polygons, generated from measured points overlaid on a second Voronoi diagram of measured points plus the unmeasured location to predict cell values. So if you look at the example on the right, the black lines represent the first Voronoi diagram. And then a second Voronoi diagram is generated by using the sample points plus the location that I'm trying to predict. And that generates the red Thiessen polygon within the Voronoi diagram that I can utilize to identify my natural neighbors. Now, natural neighbors are measured polygons overlapped by the unmeasured Thiessen polygon. And weight is a function of the proportional overlap of adjacent polygons. So in the example on the right, you can see that the sample points to the northwest and the northeast have more influence on the predicted value of the yellow location than the sample points to the southwest and the southeast. Now, natural neighbor is an exact interpolator where values are guaranteed to be within the sample min-max values. Spline is a deterministic interpolator that predicts cell values based on the degree of smoothing. We use the spline geoprocessing tool for sample points that represent a smooth surface, for example, contours. Spline applies a mathematical function to predict cell values. The higher the weight, the smoother the surface. It's an exact interpolator where the raster surface must pass exactly through the data points, but can exceed the sample min and max values, and it has a minimum curvature. So, for example, if you look on the far right-hand side, I have those black sample points in which I use the spline tool to generate a curved line that joins all of the sample points. Of course, it's an exact interpolator, so the sample point value at any one location is represented in the raster with that same value, but the line, which is that red line in there, represents the predicted values between the sample points. And notice on the very right-hand side of the splined line, the predicted values exceed the maximum value for the sample point. And that's because, right, spline can exceed the sample min and max values. So once you've created your splined line between the sample points, you can use that to predict the values between the sample points and generate your raster surface. The last type of deterministic interpolator we're going to talk about is trend, which we can also use to predict cell values based on the degree of smoothing. We use the trend geoprocessing tool for sample points with gradual variations. It applies a global polynomial to predict cell values by applying a best fit linear trend, which is a first order polynomial, or curved trend line, which is a multi-order polynomial, to connect measured values. It's an inexact interpolator that fits a smooth, linear, or curved raster surface. And so if you look at the example below on the left-hand side, I've got a first order polynomial in which I have a series of points, and then I'm drawing a best fit line between them. So it generates a flat or sloped surface. In this example right here, notice again that's an inexact interpolator. So the predicted values don't necessarily have to intersect the sample point values. In a multi-order polynomial, the best fit is a curve that you're trying to fit to the sample points to create the predicted value. In this example right here, I've got a valley, so I'm using a second order polynomial to fit a line that best represents the sample points in my graph to generate my raster output. Now, in addition to deterministic interpolators, we also use geostatistical interpolators that predict cell values based on spatially autocorrelated points. And again, what that means is points that are within close proximity to each other are most likely to be closer in value, and points that are spread out are less likely to be close in value. So deterministic versus geostatistical interpolators. Deterministic predicts surface from measured points. Geostatistical predicts surfaces from random points compared to the statistical properties of measured points. So rather than predicting a surface directly from the measured points as you do in deterministic, geostatistical analyzes the statistical properties of the measured points to then generate the surface. The outputs of a geostatistical interpolation include the prediction surface, which both deterministic and geostatistical do that, but a benefit of geostatistical, it also generates the error or uncertainty surface. So you can actually quantify how accurate your predictions are. In geostatistical analysis, you're using the data twice. First, you're uncovering the dependency rules or the correlation between your data, and then you're making predictions based on that. If you look at the example on the right, I have a semi-variogram, which basically maps the distance against the difference in value for each unique pair of points. So for example, on the far left-hand side of the variogram, those points are both in close proximity and close in value. And when you get all the way out to the far right-hand side of that diagram, the points are no longer close in distance or close in value. Now, all geostatistical interpolation falls within the Kriging family. So in ArcGIS Pro, when you look at the interpolation tool set, you'll find that you have your deterministic interpolators, but there also is Kriging, which is a geostatistical interpolator. So we use the Kriging geoprocessing tool for sample points where spatial proximity and directional bias is used to predict values. You see Kriging used a lot in energy exploration where they'll sample thousands of feet down and find certain types of geologic formations that they're interested in. And they know that there is some natural directional bias and spatial proximity to those geologic formations. So Kriging assumes measured points closer in distance or closer in value. And if there's a negative correlation between the sample points, it indicates dispersion. If there's a positive correlation, it indicates clustering. And if there's a neutral correlation, it indicates randomness. Now, Kriging is a very complex multi-step process in which first you map the data in GIS, then you explore the data with statistical tools, you fit a model to create a raster surface, and then you perform diagnostics to evaluate the model. And if you want to know more about geostatistical interpolation, I suggest you take our Advanced Problems in GIS class, where we have a whole competency and a real-world project where we focus on deterministic and geostatistical interpolation.